From the dawn of human consciousness, we have gazed at the stars and wondered about our place in the cosmos. One such enigma is the concept of infinity, a concept that has puzzled philosophers and scientists for centuries. Imagine a universe that is not a straight line stretching infinitely into the distance, but rather a circle, a sphere, a shape that curves back on itself. In this universe, there are no edges, no boundaries, no points where space simply ends. This concept, though seemingly strange, offers an elegant solution to the paradox of infinity. If we entertain the idea of a closed universe, then the question arises, what happens at the end of this cosmic sphere? The Big Crunch is a hypothetical scenario in which the expansion of the universe eventually slows down and reverses. This is the idea behind the Big Bounce, a cyclic model of the universe in which the Big Crunch is not the final act, but rather the prelude to another Big Bang. The idea of a closed universe with its Big Crunch and Big Bounce offers a captivating and elegant alternative to the more traditional view of an infinite, ever-expanding cosmos. It resolves the paradox of infinity, provides a potential mechanism for the universe's beginning and end, and even hints at the possibility of a universe reborn from its own ashes. The journey toward understanding our universe is paved with bold ideas and a willingness to challenge our assumptions. In the heart of our reimagined universe lies a structure of profound mystery and unimaginable power, a wormhole. Imagine, if you will, a bridge connecting two seemingly distant points in space and time, a shortcut through the very essence of existence. The wormhole, by connecting the beginning and end of the universe, hints at a universe that is not linear but cyclical. To truly grasp the implications of a wormhole connecting the Big Bang and Big Crunch, we need to expand our understanding of the universe's shape. Imagine for a moment not a flat, boundless expanse, but rather a more familiar, yet in this context, extraordinary shape, a donut. This torus model elegantly addresses the paradox of a finite universe with no boundaries. Our current understanding of the universe is shaped by the observation that galaxies are moving away from us. However, in our closed, torus-shaped universe, this expansion takes on a new meaning. This concept of local expansion within a globally static universe provides an elegant solution to the question of where the universe is expanding into. The vastness of the universe, even in our observable patch, is almost incomprehensible. However, in our closed universe model, this perception of infinity is an illusion, a consequence of our limited perspective. The true nature of the universe, with its closed geometry and finite extent, is revealed only when we consider the possibility of a larger, unseen cosmic structure. The concept of a closed universe, with its torus shape and wormhole connections, challenges us to rethink our most fundamental assumptions about the cosmos. This inward focus, rather than diminishing the grandeur of the universe, actually amplifies it. The true nature of the universe, with its closed geometry and interconnected regions, might be far stranger and more awe-inspiring than we ever imagined. One of the most fundamental laws of physics is the law of conservation of energy. In our closed, torus-shaped universe, the conservation of energy is not violated, but rather beautifully maintained through a delicate cosmic balancing act. This elegant cycle of creation and destruction, expansion and contraction, ensures that the universe's energy budget always balances. In the ongoing quest to unravel the mysteries of the cosmos, scientists have discovered a perplexing force that seems to permeate the universe, driving its expansion at an accelerating rate: dark energy. In our closed universe model, dark energy takes on a new significance. The expansion we observe, attributed to dark energy, could be a localized effect caused by the curvature of space-time in our region of the torus. The concept of a closed universe, with its interplay of expansion and contraction, leads to a fascinating possibility: a universe where the total energy content is zero. This might seem counterintuitive. After all, the universe is filled with stars, galaxies, and countless other forms of matter and energy. How can all of this add up to nothing? The answer lies in the way we account for energy, particularly gravitational potential energy. Gravitational potential energy is the energy an object possesses due to its position within a gravitational field. It's a form of stored energy, ready to be released when the object moves closer to the source of gravity. In a closed universe, the gravitational potential energy is negative, counterbalancing the positive energy associated with matter and radiation. Imagine two massive objects, like stars, being pulled towards each other by gravity. As they move closer, their gravitational potential energy decreases, becomes more negative, while their kinetic energy, energy of motion, increases. In a closed universe, the total energy, the sum of their kinetic and potential energies, remains constant, even as energy is exchanged between these forms. The torus model of the universe, with its wormhole connecting the Big Bang and Big Crunch, suggests a dynamic cosmos, a universe engaged in a perpetual dance of expansion and contraction. This cosmic ballet, far from being a chaotic affair, is governed by the precise laws of physics, a delicate interplay of gravity, energy, and the curvature of space-time. Imagine the universe as a vast, interconnected web, with each point on the torus representing a different region of space and time. As one region expands, stretching the fabric of space-time, another region contracts, drawing energy and matter inwards. This dance is not random. It's choreographed by the geometry of the torus itself. The wormhole, acting as a cosmic conduit, channels energy and matter from regions of expansion to regions of contraction, ensuring a continuous flow, a cosmic circulation that maintains the universe's energy balance. This dynamic interplay between expansion and contraction is not a flaw in the universe's design, but rather an essential feature, a testament to its elegance and complexity. The idea of a cyclic universe, one that undergoes periods of expansion and contraction, birth and rebirth, has resonated throughout history, appearing in various forms in different cultures and mythologies. From ancient Hindu cosmology, with its cycles of creation and destruction, to the Ouroboros, a serpent or dragon eating its own tail, symbolizing eternal return, the concept of a cyclic universe has captivated the human imagination for centuries. In our torus-shaped universe, this ancient idea finds new life, supported by the principles of modern physics. The Big Crunch is not the end, but rather a new beginning, a cosmic reset leading to another Big Bang. This cycle of expansion and contraction, birth and rebirth, could repeat endlessly, a testament to the universe's resilience and creativity. This cyclic model has profound implications for our understanding of time. In a cyclic universe, time is not a linear progression from past to future, but rather a cyclical journey, a cosmic loop where the end is also the beginning. This concept, while challenging our intuitions, offers a captivating glimpse into the potential nature of a universe that is both finite and eternal. Time, that relentless river, seems to flow in one direction, from the past through the present, towards the future. This perception of time's arrow dictates the rhythm of our lives, from the beating of our hearts to the rise and fall of civilizations. Yet, in the grand cosmic ballet, the nature of time takes on a more nuanced character. What if this flow of time is but an illusion, a consequence of our limited perspective? Imagine standing on the surface of our cosmic donut, where the Big Bang and Big Crunch are recurring chapters. From our vantage point, time seems linear, but we are caught in the current of time's river. Just as a river's current varies, so might the flow of time be influenced by space-time's curvature. In our everyday lives, we rely on clocks to measure the passage of time, to synchronize our actions, and to navigate the rhythms of our world. But what is a clock, really? It's a device that measures change, a system that undergoes regular, predictable transformations that we can then use to track the flow of time. But in a universe where time itself might be a more fluid, less absolute concept, the idea of a universal clock, ticking away the seconds uniformly throughout the cosmos, becomes questionable. Imagine each point on our cosmic torus, each region of space-time, having its own unique clock, each ticking at a slightly different rate, influenced by the local curvature of space-time, by the proximity to regions of expansion or contraction. These clocks are not independent entities, but rather interconnected parts of a grand cosmic symphony, their individual rhythms harmonizing to create the music of time as we experience it. Some clocks might tick faster, others slower, and some might even seem to run backward from our perspective, depending on their location within the torus and the complex interplay of gravitational forces. The concept of an infinite universe, stretching out forever in all directions and existing for an eternity, can be both awe-inspiring and unsettling. The implications of such a vast, timeless expanse challenge our ability to comprehend our own existence, making us feel insignificant and ephemeral in the face of such immensity. But in our closed, torus-shaped universe, the problem of infinity is elegantly resolved. Time, like space, becomes finite yet unbounded, a cosmic loop rather than an endless corridor. Imagine walking down a seemingly endless hallway lined with countless doors, each representing a moment in time. In an infinite universe, this hallway would stretch out forever, an intimidating and ultimately meaningless journey through an endless succession of moments. But in our torus universe, this corridor, while vast, is ultimately finite. If you were to walk long enough, you would eventually return to your starting point, having traversed the entirety of time's cycle. The end of the corridor would lead back to the beginning, the Big Crunch merging seamlessly with the next Big Bang. We often think of time as a fixed, unchanging backdrop. But what if time itself is not so rigid? What if, like shifting sands, time is constantly reshaping itself? In our torus-shaped universe, space-time is stretched and compressed. Time might flow faster in some regions, slower in others. In a universe where time is cyclical, the past is not gone, merely recycled, its echoes reverberating through the vastness of the cosmos. Imagine the fabric of space-time retaining a memory of past events, faint whispers and ghostly imprints embedded within existence. These echoes might manifest as faint patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. Cosmologists might one day decipher these cosmic echoes, uncovering clues about the universe's past cycles. The vast emptiness of space is not as empty as it appears. Hidden within this void, a sea of quantum energy churns, where virtual particles flicker in and out of existence. This is the quantum vacuum, a realm of immense energy density. Quantum mechanics revealed the vacuum to be anything but empty. It teems with virtual particles, pairs that pop into existence and annihilate each other. The energy density of the quantum vacuum is thought to be enormous. The quantum vacuum might seem purely theoretical, an artifact of our equations rather than reality. But nature reveals its secrets through the Casimir effect. Imagine two metal plates in a vacuum. They experience a tiny but measurable attractive force. Named after Hendrik Casimir, this force arises from the quantum vacuum. The Casimir effect provides crucial insight into the quantum vacuum on a cosmic scale. It shows the vacuum's energy density is real and measurable. This has profound implications for understanding dark energy. Could dark energy be the quantum vacuum's energy density? In a torus-shaped universe, this idea gains significance. The torus model helps explain how vacuum energy density drives cosmic expansion. Section 4, Mapping the Cosmic Echoes. The torus model suggests a universe where the past is recycled, its echoes imprinted in space-time. These echoes might manifest as faint patterns in the cosmic microwave background radiation, like ripples in a pond. The Big Bang creates ripples in space-time, detectable with sensitive instruments. Mapping these echoes could reveal the hidden geometry of our universe. The Cosmic Symphony of Constants. Our universe is a marvel of balance, governed by fundamental constants that dictate everything from gravity to light. These constants determine the properties of every atom, star, and galaxy. Imagine a grand cosmic symphony, shaped by the fundamental constants of nature. The gravitational constant, like a deep bass drum, shapes the universe's structure. Together, these constants create the symphony of the cosmos, a testament to the universe's precision. Section 2. A universe fine-tuned or finely tuned? The remarkable fine-tuning of the universe's constants has puzzled scientists and philosophers for centuries. If even the slightest tweak to these constants would render the universe lifeless, how did they come to be so perfectly calibrated? This question, known as the fine-tuning problem, has led some to invoke the anthropic principle, the idea that the universe must be fine-tuned for life because we are here to observe it. Others have proposed the existence of a multiverse, a vast ensemble of universes, each with its own set of physical constants. In this scenario, our universe is just one of countless others, and its fine-tuning is simply a matter of chance. We happen to live in a universe with the right conditions for life, while countless others remain sterile and unobserved. However, the torus model, with its closed geometry and cyclical nature, offers a compelling alternative to these explanations. In our torus-shaped universe, the Big Bang is not a singular event, but rather a recurring chapter in an eternal cosmic story. Each cycle of expansion and contraction, each birth and rebirth of the cosmos, provides an opportunity for the fundamental constants to readjust, to explore new values and configurations. Imagine a cosmic dance with the fundamental constants as partners, their movements guided by the underlying laws of physics, yet free to explore new possibilities within the confines of the torus. Each cycle could be seen as an experiment, a trial run in which the universe tests out different combinations of constants, searching for a configuration that leads to stability, complexity, and ultimately, life. This dynamic view of the fundamental constants has profound implications for our understanding of the universe's evolution. It suggests that the universe is not static, not frozen in a particular configuration, but rather constantly evolving, constantly searching for new and more complex forms of expression. The torus model, with its cyclical nature and dynamic constants, offers a captivating vision of a universe engaged in a grand experiment, a quest for cosmic harmony. Each cycle, each iteration of the cosmos, represents a step in this quest, a refinement of the universe's ability to support complexity, diversity, and life. This quest for harmony might not be random or aimless. It might be guided by underlying principles, by a deep-seated drive within the very fabric of existence to explore all possibilities, to manifest its full potential. The torus model, while speculative, provides a framework for understanding the universe's fine-tuning, not as a lucky accident or a sign of a multiverse, but as a testament to the universe's remarkable ability to self-organize, to learn from its past cycles, and to evolve towards ever-increasing complexity and harmony. It is a vision of a universe that is not static, but alive, a universe engaged in a perpetual dance of creation, destruction, and renewal, a testament to the boundless creativity and mystery of existence itself. We've embarked on an extraordinary journey, a voyage not through the vastness of space, but through the even more expansive realm of ideas. We've challenged our preconceived notions of the universe, venturing beyond the familiar and often comforting picture of an infinite, ever-expanding cosmos. In its place, we've envisioned a universe that is finite yet unbounded, a closed system elegantly balanced between expansion and contraction, birth and rebirth. This torus-shaped universe, with its wormhole connections and cyclical nature, is more than just a mathematical curiosity. It's a radical reimagining of our place in the cosmic order, a shift in perspective that has profound implications for our understanding of time, space, and the very nature of reality itself. The torus model paints a picture of a self-contained universe where energy and matter are recycled, flowing from regions of expansion to contraction, fueling the cosmic dance. Creation and destruction are ongoing processes. This resonates with ancient myths and modern physics. Imagine a cosmic engine powered by fundamental forces. The expansion of our universe is part of this cycle. Elsewhere, regions are contracting, preparing for the next Big Bang. In a torus universe, time is a loop, a cosmic Mobius strip. The past, present, and future are intertwined in a cosmic dance. The torus model, while elegant and compelling, remains a theoretical construct, a tantalizing possibility awaiting experimental verification. But how do you test a theory that encompasses the entire universe, a theory that extends far beyond our observable horizon? The answer, as with many profound scientific questions, lies in finding subtle clues, faint echoes of the torus's hidden geometry imprinted on the cosmos we can observe. One promising avenue of exploration lies in the study of the cosmic microwave background radiation, the afterglow of the Big Bang. If the universe is indeed a torus, then the CMB should bear the imprint of its unique geometry, subtle patterns and variations that reflect the way sound waves propagated through the early universe. These patterns, like whispers from the dawn of time, could provide us with clues about the universe's true shape, its size, and even its history of expansion and contraction. Just as geologists study seismic waves to probe the Earth's interior, cosmologists are analyzing the CMB's subtle variations, hoping to unlock the secrets of the universe's hidden geometry. The torus model, if proven correct, would revolutionize our understanding of our place in the cosmic order. It would mean that our observable universe, vast as it seems, is just a small part of a much grander, interconnected cosmos. It would mean that we are not isolated observers peering out at an indifferent universe, but rather integral parts of a dynamic, evolving system connected to every other point in space and time. This realization, far from diminishing our significance, actually amplifies it. It suggests that we are not insignificant specks in a vast, uncaring cosmos, but rather active participants in a grand cosmic experiment, a universe constantly exploring new possibilities, new forms of complexity and beauty. The torus model invites us to see ourselves as part of a larger story, A story that extends far beyond our limited human perspective. A story that has been unfolding for eons and will continue long after our sun is burned out. A story written in the language of stars and galaxies, black holes and wormholes. A story that we are just beginning to decipher. The quest to understand the universe is a journey without end. Each answer leads to more questions, each discovery revealing new mysteries. The torus model reminds us that the universe is a place of endless wonder, a realm of infinite possibilities that will inspire our curiosity for generations. As we explore the cosmos, we must remain open to new ideas, new ways of understanding the universe and our place within it.